be more chaotic than the one on chaos because of late minute changes and general poor sleep hygiene, which I compensate by drinking coffee, which doesn't make me awake, but more on the edge, and so sleep even worse. So it's a negative, it's a gravithermal catastrophe. But we'll get to dynamics later. We'll connect the gravitational wave part of this talk, of this meeting, to the dynamics part I discussed last time. And then I will also talk about the AGN channel, which is a channel for gravitational waves that connects both the planetary physics and the gravitational wave one. No, here. All right, so let's go back to this plot that I think Philippe already showed. This is the current landscape of gravitational wave observations. What you see here is just a mass, the various masses of the progenitor black holes that have been observed merging in the universe, with the final mass of the progenitor. The x-axis is just for aesthetics. And of course, this is good, but as astrophysicists, we want to do something with it. And the main things, yeah, you can do a lot of things, of course. There are a lot of potential, because it's a new window of the universe. But from the point of view, so you can do cosmology, you can do solid-state physics, you can do general relativity, constrained general relativity theories. But as an astrophysics, we want to use this new window to probe different environments. Okay. How do we do it? Well, we have to consider, first of all, that this is very different from electromagnetic observations. So we don't count photons or gravitons. So we have to actually see the amplitude of the wave, not the power. And the second aspect is that, at least for LIGO, LIGO Virgo detection, we can see only what we expect to see. And the analog is that as if we were able to see supernova just if we knew how the light curve of a supernova would look like. And the reason why is because of the way we detect gravitational waves. As Philippe already mentioned, is that we use this template, this match filtering. So we kind of cross-correlate, we autocorrelate a signal, a known signal from general relativity with the noisy signal. And then if there is something will pop up as in the upper panel. So if it has enough signal-to-noise ratio. So it's very important for us to know how the signal looks like, and also know what are the astrophysical priors that determine the properties of the signal. Okay. So the main idea is to use this to connect the property of the signal to original environment. And one way to do it is to just look at population of at the entire population of mergers. So what we can extract from the gravitational wave signal are the masses, the spins and the orientation, the merger rate, so how frequent they are, but also the eccentricity in principle, and also the distance localization. Although at the moment we are limited to the local universe, and the localization is very, very coarse. But things will improve, of course. So at the moment, what we do for trying to understand where these kind of mergers come from, because we have no idea, is to just look at population statistics. So let's say if I predict that in one channel, the eccentricity, all the binaries should have eccentricity 1 or 0.1 when they enter the band, the observable band, then we can maybe connect this channel to the observations. Another way that we can use is to measure environmental effects on the gravitational waveform itself. So in the previous case, we are just assuming that these binaries merge in relative isolation. So the waveform, the signal, is exactly as what we expect from an isolated binary. But the properties of the binaries are conditioned by the original environment. In this case, the binary actually merges in a crowded environment with some other stuff. So it's not in complete isolation. So what I show here is the strain of a eccentric binary. I just calculated a few minutes ago. And if I add a perturber, that's how it becomes. So you can see that if there is a perturber, in this case it's just a tertiary body, you can have gas, you can have dark matter cast, for example. You can change the waveform, and if we find this if you can detect this kind of change, we can maybe connect the merger, a single event this time, not the population, but every single event to a scenario, to a merger channel. The main problem with this is that our current gravitational wave observers, we still have too much noise, and by the time we detect a merger, an in-spiral, we really detect the last few cycles. So we need at least more cycles in order to detect this kind of, let's say, effects, environmental effects. Yeah. So there are quite a few formation scenarios that have been proposed so far. We can summarize them in this nice category. Nice. Also, we have the dynamics scenario, the gaseous environment scenario, and the isolated binary evolution scenario. And each of them has their subset, and sometimes they also kind of mess with each other. And then their said and isolated is the non-astrophysical scenario on primordial black holes. I generally work with dynamics, but it's very difficult not to stray into other things. So I've done quite a few things so far, and nowadays I'm actually focused mostly on the galactic nucleus scenario. But I want now to connect these to tell you a bit more what the merger looks like if they come from the dynamic scenario, and I will connect to the processes I talked last time. Okay. Any questions so far? Okay. So, dynamics, basically, as I told you earlier, it's we tend to produce gravitational wave binaries that merge within the edge of the universe with this process mainly. Three-body encounters, of course, not also 4 bodies, 5 bodies in principle, but we usually focus on the simplest things. So three-body encounters that happen at the center of stellar clusters. And I've showed you last time that stellar clusters have this instability. Every self-gravitational system has an instability that causes them for the core to collapse and become more dense, while the halo expands. And there is a sort of an equilibrium, a bit like stars, that the core becomes populated by black holes that interact gravitationally and then generate energy, kinetic energy, to power the expansion of the halo. And this is a form of equilibrium in the sense that if the halo expands too much, then, no, actually, if the core generates too much energy, it will expand too much. So the density lowers, the rate of interactions decreases, a bit like stars, like nuclear reactions in the core of a star. And so the key idea of this kind of process is that these interactions can pump up the eccentricity of binaries and can also shrink them. And there is actually a statistical law called Higgs law that says that if the kinetic energy of the incoming single, let's say this is the incoming single on the left, and the binding energy of the incoming binary, which is the binding energy, so it's positive, Gm1 m2, oh, horrible, Gm1 m2 divided by A2. Okay, so if the average kinetic energy of incoming particle is lower than the binding energy of the binary, your binary will shrink on average. So statistically, the binaries that are hard, they're gonna shrink and shrink and shrink until they basically merge or get kicked out. And I showed you last time this kind of plot. And what you see is exactly the gravothermal instability and the core collapse that proceeds. Then you have these oscillations that powered by three-body encounters and few-body encounters, while the halo expands due to two-body relaxation. Okay. Why is white? Okay, yes. And this is a sort of equilibrium. And eventually, you tighten up all the binaries until they get ejected or they merge. And if a binary gets ejected, you immediately form one if the halo expansion requires energy from the core. Okay. And yes, so given this process, we can imagine what are the properties of mergers from this channel. And one main property is that, for example, is that when you have this chaotic three-body encounter, you tend to eject the lightest body. You keep the most massive one, because it's easier to eject lighter particles. So what you have in reality then is that your distribution of mass ratios, so for objects, for binaries that remain, tends to be close to 1. And this is a plot from a paper from collaborators that shows that from simulations that binary black holes that merge within the age of the universe from young massive star cluster. They have these pink and orange and blue distributions, which is picked as a 1. So more or less, you tend to pair black holes that have the same masses. And accidentally is also, in the gray shaded area is also the isolated binary channel, which also actually says that you should expect equal mass ratio binaries. But I won't talk about it today. So another property is that you can, if you can retain the merger products. So if you can retain a merger product of the black hole, you can maybe merge these with another black hole, and so you can build up mass. This is something that you can use to overcome some certain barriers that I think Filippo talked about, like the peri-instability gap, where the whole star simply blows up, and so we don't expect any black holes in that mass range, just because, but from isolated evolution, not from dynamics, for example. But I will talk about it later. And the eccentricity is the most important feature of the dynamical channel. And in this plot, you see the expected eccentricity distribution when these binaries enter the observable band. And all these sub-distributions all come from the dynamical channel, but from different sub-channels, from different kind of trajectories or interactions. So the most eccentric binaries are the ones that come directly from three-body interaction. So you have a chaotic interaction. Suddenly, two black holes meet in a hyperbolic passage, but they meet too close, so they radiate away gravitational wave energy, and they merge immediately. So these are the most eccentric ones, because when you have, let's say, a hyperbolic passage between two black holes, you basically have to go from an eccentricity that is greater than 1, because this is hyperbolic orbit, to an eccentricity that is lower than 1. So eventually, here you radiate a lot of energy, and since this distance has to be very small for this process to be efficient, then what happens is basically you have a very, very fast plunge. And can be shown analytically that basically you expect a very eccentricity, very high eccentricity, very close to 1. Then you have other kind of type of mechanisms that all happen in this case, globular clusters. So for example, as I said earlier, you can eject binaries. In this case, they simply got ejected because of dynamical interactions, and they will merge in isolation. So they're outside the cluster. They have become isolated binaries. But we don't see them because they are black holes already. In clusters means that maybe the binary was ejected. So these are, let's say, these are the, what's called ejected. So sometimes you can kick out a binary, but it will still remain bound. So it will take some time to come back. And in this case, I think that's the green distribution. So no, wait, in cluster distribution. So the binary is still in cluster, but it merges in, maybe not in isolation, but it's considered as it was in isolation. And then you have primordial binaries. These are binaries that have been not dynamically formed. So they have not been formed through dynamical interaction, but they were primordial binaries in the beginning. They were stellar binaries, and they remained somehow, they avoided all the interactions with other stars. They remained primordial, and they merged on their own. Okay. I think I covered all the 4 colors. Any questions so far? Yes. Yeah. Yeah. Yes, exactly. So yeah, these ones, and also these ones in a sense, because these basically, so this one, they have a gravitational wave coalescence timescale. Okay, yeah, that is more shorter than the age of the universe. This one have a gravitational wave rate time scale that is shorter than the time return time, let's say. And the return time depends on the property of the cluster as well, because this binary won't simply just come back, but it will feel the gravitation, so it will tend to do like this, you know? It's not gonna go just back. And then it will slowly sink in due to dynamical frictions, equipartition, and so on. Yeah. Any other question? Okay. Yes. So another important parameter we can extract from gravitational wave signal is the chi-effective spin that you played with the data some time ago, a few days ago. And so if you imagine that all these binaries got mixed by three-body interactions, you should not expect any correlation between the spins, because you pair isolated black holes, you change the orbital plane, and so you should expect completely isotropic distribution of chi-effective. So in general, if you have uniform obliquities, you should expect a chi-effective distribution that is centered on 0, all right? So this plot, yeah, should be perfectly centered on 0. You have a equal balance of binaries with anti-aligned spins, so have negative chi-effective, and binaries that have positive chi-effective, so they are aligned. Okay, but there is a caveat, is that we have primordial binaries in the cluster. Okay, so primordial binaries can have aligned spins. Okay, and if they have aligned spins, it means they are correlated, and this should have positive chi-effective, so with no obliquity. But if these primordial binaries are part of the cluster, they might get perturbed by other tertiary bodies. And so in principle, this can generate some spin-orbit alignment. So actually, no, spin-orbit misalignment. So you can perturb the binary orbit. The spins will remain the same. And this is basically the kind of analysis that you've done with the binaries that you analyzed a few days ago. There were a set of binaries that were coming from isolated binary evolution, so primordial binaries, and the same binaries, but after a single three-body encounter. And what I was expecting from your data analysis was something a bit like this, so that originally the primordial binaries can only have positive chi-effective because they have aligned spins. Yeah, by the way, I didn't mention why they should have aligned spins, but it's basically due to tidal spin up. So if you have two cores very close to each other, will tidally circularize, and the spin will synchronize to the orbit, just like with the moon and the Earth. And so eventually, you tend to have the equilibrium state is with spin aligned, just like the Earth and the moon. And so what I was expecting is that if you have a single three-body encounter, then you cannot really erase this alignment. So you still keep some correlation, so you can create an asymmetry in the chi-effective distribution. And this is actually much closer to what is observed nowadays. So nowadays, there is a chi-effective distribution, which is kind of like a Gaussian centered a little bit above 0. And this is kind of difficult to explain with the pure dynamical channel, because we don't expect any asymmetry in any preferential direction in the spins. Questions? Okay. So, but dynamics, in the dynamical channel, we have the chance to build up massive black holes, because if you can retain the merger product and doesn't get kicked out, it can meet other black holes and produce what we call second generation, actually first generation, second generation, and so on. So first generation actually refers to the first merger product between two black holes that comes from stars. Second generation is between first generation black holes and so on. So in principle, this seems a wonderful idea to make intermediate massive black holes, or who knows, even supermassive black holes. But there is a caveat. The caveat is that the black hole spins increases with mergers. And the reason why is that when you or you merge two black holes, let's say you spin, yeah, let's say that they are even spinning, let's say, and this is the orbital angular momentum. So when they merge, so at the first they will in spiral. At some moment they will plunge, and at the moment of the plunge, the spin of the new black hole will inherit basically the sum of the spins, individual spins, and the sum of the S1 plus S2, and also the orbital angular momentum. Okay, and the idea is that this will, even if you start with non-spinning black holes, what you have at the end is let's say from an equal mass merger between two black holes that are non-spinning, the final spin of the black hole is going to be very close to 0.7. But this is also statistically true for spinning black holes, simply for the reason that, okay, if you merge, if your spins are aligned with the orbit, then the spiral can go much farther in. So the boundary will plunge when it's much, much closer. So eventually, the angular momentum is less. While if you have this other scenario, if you have anti-aligned spins, so if the spins point on the opposite side with respect to the angular momentum of the orbit, the plunge will happen much earlier. So let's say that this is the moment of the plunge, and it will happen much earlier. So eventually, this orbital angular momentum is larger. So even if it gets subtracted away by the individual spins of the black holes, then eventually, you obtain, on average, a spin of 0.7. And this is still considering single mass spectrum, so equal masses. And so you can see from this plot, these are distributions of first-generation merger. Yeah, first-generation merger black holes. You can see that there is a distribution, of course, because there is a distribution in masses. They shouldn't be spinning. And then, if you merge these blue black holes with among themselves, you obtain the yellow ones. And you see that the yellow ones have a chi-effective that is very close to 0.7. They spin quite fast. Okay, what this has to do with the retention of black holes? The problem is that if black holes are spinning and they merge, they have a gravitational wave recoil kick that is shown here. This is for the same population in the previous plot. So these recoil kicks will kick the merger product in some random direction, and they can go up to 1,000, even 2,000 kilometers per second. So if you think about that, the velocity dispersion of the biggest nuclear star cluster is about 50 kilometers per second. You can see that there is no way of retaining these merger products inside the cluster. Okay. But you can do it. You can do it. Maybe there is a chance to retain these merger products in nuclear star cluster. And we are with a student from Northwestern University. We did this paper using some Monte Carlo way of modeling these interactions. Nuclear star clusters are very massive, have so many particles, so we cannot really model with embodied codes yet. And not even with Monte Carlo codes, we kind of do some tricks to speed up the integration of particles by using simply integrating them in the Mill field and then adding on top some relaxation in using some tricks. So not even Monte Carlo code can model this massive 10 to the 8, 10 to the 9 solar masses nuclear star cluster. But so we have to do something different, only considering a limited set of bodies. And what you see here is basically the mass. You can see them as the mass. The one corresponds to 1,000 solar masses. And the more massive you have, the tracks are basically individual tracks of a seed, of a black hole seed that we put at the center of the nuclear star cluster. And as time passes, you see that there is a possibility for this runaway, that your black hole will meet other black holes, and then eventually, by chance, because of the orientation of the spin, it gets retained in the cluster, and eventually builds up to 1,000 solar masses, so it becomes an intermediate massive black hole. Questions? No, good. And what we saw basically is that the main barrier is the third generation, second generation. Once you reach 7 mergers, your seed is so massive that even if it merges with a smaller mass black hole, it's not going to get kicked out of the wave. Okay. Okay. Any question on the Lamical channel? Because now I'm going to move to the active galactic nuclei channel. Yes. Yep. Yeah. So this is just some rare episodes that you can actually build up the mass. So yeah, so this is the kind of rapid increase. It's a runaway process that you can still build up the mass in global cluster, very massive nuclear star cluster actually. But yeah, what I didn't show is that the fractions, the probability for this to happen is like 1%. So in 99% of the times, our black hole seed gets ejected. In those 1% of cases that this doesn't happen, what you see is this is a runaway process that you can build up to 2,000 solar masses in less than a giga-year. So this is very fast, very, very fast. But it's rare, yeah. What you don't see here is that it's actually rare. Yes? A bit less, because we have a mass spectrum of black holes. Yeah, but only one seed. In this case, the seed was 50 solar masses. 50 mergers, yes, yeah, at least, yeah. Yeah. You are producing a non-negligible amount of gravitational waves. Yes, of course, yes. Yeah. And yes, exactly. And actually, what we see is that there is a mass gap. So imagine that you basically have two cases. Either you stop at the third generation because you get kicked out, or you get over this barrier and you build up get a runaway merger. This has happened to 1%. Doesn't this violate already the bounds we have by observation? Yeah, this paper we didn't really calculate the rates. No, we didn't really calculate the rates. We have to factor in that these star clusters are very, very massive. These nuclear star clusters are really huge. So you see that, for example, 10 to the 9 has quite many, but for 10 to the 8, it's very few. And we don't even show 10 to the 6 and 10 to the 7 because there was no runaway, basically. And yeah, we should do some rate calculation and integrate what is the nucleation fraction of galaxies. How many have a nuclear star cluster? How many have a nuclear star cluster so big? And then estimate the merger rate. Yes. Yeah. Yeah. No, this is already 30 pages long paper. So the referee didn't ask. Yeah. No. It was the first time that we attempt this kind of calculation because nobody has explored this regime of very massive star cluster with anything, because we cannot touch this, not even with Monte Carlo codes. Questions? No questions. Good. So, moving on to the topic that actually connects both planetary physics and gravitational waves, is what happens if you have mergers in an active galactic nucleus. So basically a big accretion disk at the center of a galaxy. And there has been there is actually a few cases that one can consider in active galactic nuclei that are interesting for gravitational wave astronomy in different regimes. So first of all, you can have double, how do they call it, binary supermassive black holes, or supermassive black hole binaries. So that can, let's say, be surrounded by an accretion disk. And these are very interesting for LISA Science and PTA. And in this case, what people have been doing is to try to see what is the environmental effect of the gas disk on the gravitational wave emitted by the double supermassive black hole. And also the secondary cases where you have a supermassive black holes, but you have stellar mass black holes around. Eventually, these stellar mass black holes will in spiral and have this extreme mass ratio in spiral. That this can be, again, observed in LISA. But what I mean is still LIGO Virgo black holes, so mergers between stellar mass black holes. And the main idea is that you, actually, let me start from the very beginning. So the main idea is that you have the supermassive black holes at the center of a galaxy. They're quite massive, and they attract a lot of stuff. So if you have a nuclear star cluster, eventually black holes will tend to sink towards the center of the galaxy and will form a cusp. So basically, if you would have a look at the density of these black holes, it would form a very steep cusp around the supermassive black hole. Just because they're the most massive objects in the galaxy, and eventually they sink in. And this is supported also by observations in our galactic center. So there might be a dark cusp in our galactic center. Then suddenly, maybe you have a wet merger, maybe you have an influx of gas from the galaxy, and you form an accretion disk. What happens is that all these black holes that were orbiting the supermassive black hole, they suddenly cross this disk. And when they cross this disk, they're gonna feel, actually it's much better drawn here. They cross the disk, they feel a shock, they undergo dynamical friction, and then they tend to sink into the plane of the disk. So they get aligned into the disk. Then the second aspect, so this is exactly the link with planetary physics, is that these black holes, once they are aligned, they will start to feel migration torques. And as Vladimir said last week, you can have both positive torques and negative torques. And if you have a region of the disk where you have a negative torque that meets a positive one, then you have a migration trap, an area, a radius where all black holes tend to migrate towards. And so you make them meet. You don't have to wait for them to just by chance meet each other. They're going to become basically migrate over the same point and interact. And so there, what happens is still kind of uncertain. I'll show you next one. And for example, we have we are using exactly the same recipes for migration that we use for protoplanetary disks. So we assume that these planets are embedded in the accretion disk. So like this, and there is a spiral density wave on this side, on this side. And then these have induced a torque. The torque cancel out, so this torque drives the planet inward, this one drives the planet outwards. Then you have a net torque, and so the black hole will go somewhere. Then there is also something else that has been added lately, is the fact that if the black hole, or the planet, is actually luminous, so is actually accreting, and this accretion is making the gas around hotter, then you have some lobes. These lobes are hot, so they are underdense. And this also causes a torque on the black hole. And this torque tends to push them outward. And so in this paper, Yevgeny Grishin showed that basically, once you take into account for all these torques, so type 1 migration, thermal torque, and so on, you can calculate that basically if you have a very massive accretion disk for a black hole greater than 10 to the 8, you don't have any migration trap. You tend to simply push the black holes out. They all push outwards. While if you are below this, then you see this is on the left y-axis is basically the radius of the disk divided by the Schwarzschild radius. And then you can actually form two traps. One is the inner anti-trap, where black holes tend to, on one side, tend to be pushed inward, and on the other side, outward. And then you have an outer trap, where actually black holes can meet. And this, I mentioned last week, but this is actually consistent with observations. So you can actually take into account all the spatial distribution of events, correlate these with the distribution of quasars, and see that actually they don't really match, especially the most luminous quasars with more than 10 to the 8 solar masses black hole, they don't really match with the events. So, but of course, this doesn't make that they actually come from AGNs. And yeah, what happens when finally two black holes meet in a trap is really not, we don't really know it yet, because you have messy gas physics. So, and actually I have a lot of physics. Yeah, you have a lot of physics going on in the presence of a supermassive black hole. You have that if your binary is inclined, your black hole will cause oscillation in the orbital elements of the binary. These are called causality of oscillations. Then you have the gas that can make the two unbound black holes that meet bound, but can also make them merge immediately. And then depends which side the two black holes are rotating. The binary can be co-rotating with respect to the disk, or be retrograde with respect to this. So there is a lot of complex physics, and actually a lot to be done. And these are some very recent papers with hydro simulation exploring what is the effect of two black holes meeting within an AGN disk. And you can imagine that this kind of scenario is very complex, so the physics that you put into this hydro simulation is very simplified. So we are still at an early stage of understanding this process, and there are a lot of PhD projects in this kind of scenario. Wait. Yes. What time is it? Okay. Well, I also did something, some kind of experiments, numerical experiments with this scenario, by considering a three-body encounter within the disk, but neglecting the gas. So the gas again is too messy for now. So let's imagine just that we have a big binary around a supermassive black hole and a single. And well, maybe they're in the migration trap. Maybe they, maybe not. Maybe they come. This disk of black holes come from other sources, which is possible. We have a disk of massive stars in the galaxy, in the center of the galaxy. So when these stars become black holes, we will have a disk of black holes at the center of our galaxy. And there are other processes that you can use to create this kind of disk of black holes. So eventually, if you actually have a binary and wait, yeah, okay, I don't have the plot. So if you have a binary and a single that meet, you can have a three-body encounter within the disk, and with the supermassive black hole. So what I wanted to check was what is the effect of the velocity dispersion. So the disk can be a bit not just be very circular. So if the orbit, so let me start from here. So yeah, two black holes, or let's say the binary black hole and the single can meet on circular orbits, and that's fine. That's what everybody has been considering. But there are many ideas that point out that these orbits should be at least a bit eccentric, maybe because of turbulence, maybe because of gravitational interaction between the bodies. So eventually what I considered was the velocity dispersion of this disk, which is very similar to a velocity dispersion in a star cluster, except that instead of being random orbits, here you have a coherent rotation. And this dispersion measures the deviation from this rotation, from this coherent motion, in terms of eccentricity and inclination. So if these bodies here have some inclination with respect to the midplane, and some eccentricity, they will meet at weird angles, and eventually the impact velocity is going to be very high. And the second aspect is that these black holes are not in isolation. So this is not like in star cluster that there is no tidal field around. We have a supermassive black hole that is totally limited in the system. So this is the classic equipotential lines for the three-body system, for a three-body problem, restricted three-body problem. You can simply imagine that you have a supermassive black hole. There you have a triple that is interacting, but this triple is bound within this Hill sphere, is called in planetary physics. So the region where these bodies are protected against the tidal field of the supermassive black hole. And it's even by considering this on the analytical, it's very difficult to understand what happens. For example, if you have an interaction, then if you're in isolation, if you have an excursion, the single can get out and then get in. But what if the system is totally limited? Maybe this single gets captured by the supermassive black hole and then escapes, and so you terminate the interaction. Or maybe not. Maybe what happens is that the single, let's say the tidal field is a barrier instead of something that captures. So your single will come back before it will bounce on the tidal barrier. So these are actually two opposite effects, which was very unclear from the analytical point of view, so you have to run simulations. Yeah, something. Yeah, this is an example of the tidal barrier that I was talking about. So if you take the moon and you give it a kick, it will escape eventually. You know, it will escape from the Earth. But before escaping, it will explore the tidal barrier, so the Hill sphere of the Earth, because it tends preferentially to escape from the Lagrangian point, where the energy is the lowest. So the speed required to exit is the lowest. So eventually, you see the moon, instead of escaping immediately, is just doing a bit of a mess, exploring this well that you can even see more or less the shape by looking at the trajectory, and eventually finally escapes from the inner Lagrangian radius. So yeah, eventually you have to run a lot of simulations. What I did use is my code that maybe I mentioned already. It's a bit complicated, but has all the physics that we need. Post-Newtonian corrections. It can model orbits very closely. It's very accurate and has a Python interface. And this is how the three-body encounter around the supermassive black hole would look like. You start from here. Actually, maybe there is a pointer somewhere. Yes. Yeah, you start from here. You don't see, but this green, no, it's not green. Orange is a binary. And then they encounter here. This is already an exchange. And then there is another exchange here. This is a final exchange, and this blue one gets kicked out. And that's where the encounter terminates. Any questions so far? No questions? I have to go on. Yes, please. Yeah. It's a bit, so it's a bit misleading if you look at the units. X-axis and Y-axis are the same, but the Z-axis is stretched a bit. Otherwise, it would be very, very difficult to observe it. Yeah, good point. But it really has also, there's some projection effect as well into it. But basically, it got ejected, and they're basically not going to interact anymore. They're unbound. But they're still bound to the supermassive black hole. Any other question? No. So eventually, what you can measure is the merger efficiency of these kind of interactions, and is also the amount of eccentric mergers. Because one key result from this scenario is that you can have a lot of eccentric mergers. And what you see here is basically the merger efficiency as a function of velocity dispersion. And this is a disk that is very puffy, very inclined, very eccentric orbit. And here is a completely circular and coplanar disk. And as expected, what you see is a transition between type of disks. So when the disk is very puffy, the black holes meet at very high speed because they are eccentric, they're inclined, so they never meet in plane. So it's a bit more difficult to make them merge. While in the coplanar disk that is completely circular, you have a very a factor of 50 or 40 more mergers, and also more eccentric mergers. And okay, so something we still don't know is what actually is the velocity dispersion of black holes in a disk. So that's why I didn't take one single value of the velocity dispersion. I just explored the whole parameter space. And the reason why is that we still don't know what are the processes that drive the eccentricity pumping and the inclination excitation of black holes embedded in disks, or even in dry disks. So yeah, so the next, then I skip this, but yes, okay. So basically, I was thinking that, yes, indeed, if you, actually, no, I'll go back. There is something missing. Well, there is the cartoon there, but somehow it got squeezed. So the main idea that points out that the black holes are in the plane of the disk and they are circular is that you have dynamical friction. So you have the effect of gas. So if the gas is circular, so the gas has plain circular velocity, but the black holes have a relative velocity with respect to it, eventually they should sink into the disk. The gas forms a wake behind them and slows them down until they have the same velocity of the gas. So perfectly circular, not inclined, not eccentric. But the problem is that AGN disks are turbulent, even more than protoplanetary disks. And the reason why they are turbulent is that you have some angular momentum transport. You have to transfer angular momentum outward in order for the mass to advect through the disk and power the supermassive black hole. So this turbulence is really required ingredients of AGN disks, of any accretion disk. And so what happens if the velocity of the gas is not actually circular? So let's say you have instead of having just a circular velocity of the gas, you have some micro random velocity field on top of this circular velocity. And what if these black holes are coupled to the gas, to this velocity field? So if the black holes tend to follow the gas because of this drag friction, this force, they will basically follow this random velocity field, this noise, these kicks due to this turbulence, these convective motions, more or less, in the disk. So eventually what happens is that you have something like this. So if you consider only the plain laminar flow of gas, eventually the black holes indeed will become fully circular and with zero inclination. So what you see on the left is the orbital properties of a single black hole embedded in the disk. And then the blue line is when you don't have any turbulent motion. So eventually, in few orbits, you just have the eccentricity drops down, the inclination drops down. The black hole simply settles into the mid-plane of the disk, circular, no problem. But if there is this random noise, this random velocity field, what happens? The black hole gets kept getting kicked, and eventually remains on a plateau. So this plateau can be quite significant, let's say 10 to the minus 2 eccentricity, which can affect, again, the properties of mergers when the two black holes meet. And this is a work in progress of mine, which I haven't published yet because this slide is empty because I forgot to add the plot. The reason why I haven't published this yet is that analytically, you should be able to recover the plateau, okay, what is the average value of this plateau in eccentricities and inclination, but in practice, somehow the eccentricity plateau is much higher than expected. So, and I can get my head around this. And this was the plot, plus slide to explain this, but too late. Yeah, something I've also been doing in the, let's say, as a side project. So something on this topic is this how to model AGN disk. So in order to model black holes within an AGN disk, you actually need to model the AGN disk first. And turned out it was not so easy. So I was borrowed a PhD student from Birmingham, Daria Gangard, by a collaborator of mine. And the project was actually to model the embedding of black holes within the disk. And then we say, okay, let's model the AGN disk first. What's the problem? Then we use the properties of the AGN disk, like opacity, density, and so on, and then calculate how is the drag force that makes this black hole sink into the disk. It was not so easy, so eventually there was no public package to model these AGN disks. It was quite not straightforward, so eventually the project became, let's make a public package to do this kind of type of disks, and eventually got published this year. And again, this is a very hot topic nowadays. There are a lot of people working on this. My idea is to actually do something on both sides, both of the AGN side and also the black hole side. So yes, model what is the effect of the AGN environment on the black holes, but also what is the effect of the AGNs, what the effect of the black holes on the AGN, because there will be some energy transfer between embedded black holes and the AGNs, and this might change the global structure of the AGN. And there are actually many PhD projects in this slide, basically. And yeah, if you have any questions or if you like to work on this, please feel free to contact me. And I think this is my last slide. Okay, this is also my last talk. So yeah, you can find some more information on my that YouTube channel, more or less. My website has been nuked, so I need to redo it. So maybe in the next few weeks, you will find more information about this project. And yeah, I want really to thank you, everybody here, both the organizers and you, the students, for this great workshop. It's been 2 intense weeks. Too much work to consider it as a vacation, but it was lots of fun. And yeah, thank you for being here.
So we still don't know exactly the signature of the AGN environment into the waveform that LIGO would detect.
No, 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 no. No, we don't know
Like you
yet.
said something about the eccentricity, but like
Yeah,
still
yeah, yeah. It's not as an individual event, so we are still. No, we don't know yet what is the effect of the gas on the waveform. No,
So it's more like on a population level for the
it's
third
still we are
generation.
still at the population level, yes. But there are some hydro simulations. The main so you should have an effect. The problem is that if you have multi-scale physics, you have so if you form a binary within the disk, you have a circumbinary disk within the disk, and the binary forms a cavity. So you have to resolve the wall of the cavity with hydro simulation, and then you have to resolve also the shear box of your disk or your disk itself. And then you also want to model the gravitational wave between the two black holes. And then you maybe run one simulation. And that's it. Yeah. No, so far, nobody has actually included all these physics, by the way. Nobody has actually included the post-Newtonian physics, for example. They only use Newtonian physics. So, but yeah, we're getting there.
And regarding that AGN code that you made with collaborators, like very naive question, but is that like too different from the codes that Vladimir presented last week?
Yeah, so actually I was in a workshop, no, it's a retreat, yes, with the planet people of my institute, the Copenhagen University a few months ago. And I actually asked them, how are our disks different than yours? So how is a protoplanet disk different from this one? And yeah, there are lots of differences, yeah. So this one actually includes way more physics than the simple power law model that Vladimir showed. Yeah.
But you don't need to consider any relativistic effects.
No, 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 no. There is no. Well, besides the fact that you have a black hole at the center, and you kind of things fall into the black hole, you don't have any relativistic effects.
Okay, are we having a hands-on later?
Not from me.
Not for you. So everybody else has vanished. So I guess today we are closing. So tomorrow we are having the standard 2 lecture in the morning. So in the afternoon we are not having hands-on session, but reconvene at 2 tomorrow because we are having some closing remarks. We are preparing a sort of summary. And so we might want to have your feedback too. So be here tomorrow at 2, and then tomorrow we close early as today. But we still have time for one question or two. Yes.
My only question is if the slides is going to be in the website.
I just upload the PDF. Yeah, exactly. Yeah.
Okay.
Yeah, definitely.
Great, thank you.
But also the videos, you can really watch the videos again on YouTube. We have a channel, the ICTP-SAIFR channel.
Yeah.
which is more followed than the Olympics. Okay, so a warm thank to Alessandro.
Thanks a lot.